Welcome. There is nothing to do now but rest. Let your eyes soften. Let your breath find its own unhurried rhythm. And let the weight of the day sink into the mattress beneath you. Tonight, we drift back through time itself, toward the oldest stars still burning. The universe is about 13.8 billion years old. It began as a single, impossibly hot point, then cooled and spread into everything we now call home. Hydrogen, helium, and a faint trace of lithium were the only elements the Big Bang produced. No carbon existed yet, no oxygen, no iron, none of the elements that make up rock or blood or bone. The infant universe was a vast, glowing fog of the simplest atoms there are, drifting quietly through an expanding dark. Everything heavier would have to wait to be born inside a star. For hundreds of millions of years, no heavier elements existed anywhere in the cosmos. The universe held only its first light gases, cooling in the dark, waiting. There was no stone underfoot, no metal, no dust. Only hydrogen and helium spread thin across an expanding void. It was a strangely bare universe, patient and unlit, before the first fires had a chance to gather. Roughly 100 to 250 million years after the Big Bang, the first stars began to gather and ignite. Gravity slowly pulled the thin primordial gas into denser and denser clouds. Somewhere inside those clouds, pressure and heat finally crossed a threshold. Light broke out across a universe that had never known light before. It was the true dawn of the cosmos. Astronomers call these earliest stars Population 3. The name sounds technical, almost bureaucratic, but it marks something extraordinary, the very first generation of starlight the universe ever produced. Everything that came after, every star we can see tonight, descended in some sense from them. They were the ancestors of ancestors, the first spark in a long, unfolding lineage of light. No one has ever directly observed a population 3 star. They lived and died so early and so far away that their light, if it still traveled toward us, would be stretched into wavelengths at the very edge of what our telescopes can catch. Their existence rests on theory, on careful modeling, and on the faint chemical traces they left behind in the stars that followed them. It appears that population 3 stars were enormous, some hundreds of times the mass of our Sun. Without heavier elements to help gas cool and clump into smaller pieces, only very large clouds could collapse at all. The result was a generation of stellar giants, unlike anything alive today, brilliant, blue, white, and almost unimaginably massive compared to the modest sun above your own sky. These giants burned through their fuel in just a few million years. It is a blink of an eye against a universe now measured in billions. Their enormous mass meant enormous pressure at their cores, and enormous pressure meant a fast, fierce rate of fusion. They lived bright and burned out quickly, trading longevity for a brief, radiant intensity that reshaped everything around them. When they died, population 3 stars scattered the universe's first heavy elements outward through supernova explosions. Carbon, oxygen, iron, and more were forged in their final moments and hurled into the surrounding dark. That scattered material drifted into new clouds of gas over time. In a real sense, every heavier atom in your body traces back to one of these ancient, radiant farewells. A star's metal content works like a kind of birth certificate. The more heavy elements woven into its light, the later it was likely born, after generations of earlier stars had already enriched the surrounding gas. The least metal-rich stars, by contrast, carry the faintest signatures of enrichment, hints that they formed very close to the beginning of everything. Their chemistry remembers what their light alone cannot say. Let your breath grow long and unhurried now, each inhale arriving without effort, each exhale releasing a little more of the day. Feel your shoulders loosen, your jaw unclench, the weight of your head sinking into the pillow. There is nowhere to be, nothing to solve. Simply follow the rise and fall of your chest until thought itself begins to blur at the edges like starlight through morning mist. Astronomers borrowed an unusual word for this chemical memory, metallicity. In their language, anything heavier than helium counts as a metal, even oxygen or carbon, elements no chemist would call metallic. It's a shorthand, really, a way of measuring how enriched a star's original gas cloud had become. The higher a star's metallicity, the more stellar generations came before it, layering the universe's chemical inheritance one generation at a time. Iron became the yardstick astronomers settled on. Because iron lines are easy to detect in a star's spectrum, its abundance compared to the sun's became the standard measure of metallicity. Scientists described this ratio using a simple comparison: a star's iron content relative to our sun. A value near the sun's own means solar-like abundance. A far lower value means a star much poorer in iron than the sun has ever been. The oldest stars carry only a whisper of the sun's chemical richness. Many hold iron levels thousands of times lower, their light shaped almost entirely by hydrogen and helium alone. Standing beside our sun, such a star would seem chemically bare, almost primordial in its simplicity. Its faint traces of heavier elements are like a few scattered words at the start of a very long book. Population 2 stars arose from gas that the first supernovae had already touched. Unlike their vanished predecessors, these stars carried faint traces of carbon, oxygen, and iron woven into their outer layers. They were still remarkably poor in heavy elements compared to the sun, but no longer entirely pristine. In their light lives the memory of an earlier generation's brief and brilliant existence. Unlike their unseen predecessors, Population 2 stars are the oldest stars astronomers can actually see and study tonight. Every ancient star confirmed so far belongs to this generation, born after the universe's very first enrichment, but still extraordinarily early in cosmic history. When we speak of finding an ancient star, this is almost always what we mean. They are living witnesses, not to the beginning itself, but to its immediate aftermath. Extremely metal, poor stars earned their own shorthand, EMP stars. Astronomers use this label for stars whose iron abundance falls below roughly 1,000th of the sun's. It is a threshold, a line drawn to separate the merely old from the truly ancient. Crossing it marks a star as a genuine relic, formed when the universe's chemical library held only its very first entries. Ultra-metal-poor stars push the threshold even further down. Their iron abundance drops below 1/10,000th of the sun's, a faintness that stretches spectroscopy to its very limits. Detecting iron at all in such a star requires exceptionally long exposures on some of the largest telescopes on Earth. Each confirmed example is treated almost like a rare specimen pulled from an ancient, careful excavation. Hypermetal, poor stars go further still, holding less than 100,000th of the sun's iron. At this level, iron becomes almost undetectable, hiding at the very edge of what instruments can measure. Only a small handful of such stars have ever been confirmed. Each one offers an unusually direct glimpse into gas that had barely been touched by any star before it. The Hiche survey opened one of the first organized searches for these ancient iron-poor stars. Conducted in the 1980s and 90s, it used photographic plates to scan the sky for a distinctive dip in a star's calcium absorption line, a telltale sign of low metal content. Thousands of candidate stars emerged from this careful scanning. Many of the ancient stars later celebrated by name were first noticed as a faint irregularity on one of these old survey plates. The Hamburg ESO survey expanded this search into a wider stretch of sky. Beginning in the 1990s, it combined a German survey plate archive with new southern sky observations from Chile. The project examined hundreds of thousands of stars, sifting for that same faint calcium signature. It yielded thousands of promising metal-poor candidates, several of which later revealed some of the lowest iron levels ever recorded. Each fresh survey seemed to peel back another layer of the galaxy's beginning. For a few breaths, let the room settle into quiet. Notice any distant sound, a hum, a settling wall, the hush of night air, and let it become a slow tide, arriving and receding, asking nothing of you. Shoulders loosen with each small wave. There is nowhere to be, nothing to solve, only this drifting hush, carrying you toward rest. Decades later, an Australian project called the Sky Mapper Survey carried this search into the digital age. Using a dedicated telescope scanning the southern sky in multiple colors of light, it flagged stars whose light suggested vanishingly little iron. Careful follow-up spectroscopy confirms several as among the most metal-poor stars ever recorded. One of its discoveries would eventually rank among the most chemically primitive stars known. The digital sky, it turned out, still held ancient secrets. A star of low mass changes remarkably little across enormous stretches of time. Its core burns hydrogen so gradually that the star's brightness and color barely shift across eons. A red dwarf shining tonight looks almost exactly as it did when the galaxy was young. There is no dramatic swelling, no sudden brightening, only a steady, unhurried glow. This slowness is precisely why such stars make such reliable witnesses to the deep past. Some low-mass red dwarfs burn their fuel with such economy that they could theoretically outlast the universe as it exists today. Astrophysical models suggest the smallest ones might shine for trillions of years, far beyond the roughly 13.8 billion years the cosmos has existed so far. None have died a natural death yet, simply because there hasn't been enough time. In a sense, every red dwarf we see is still in its youth. The universe itself is not yet old enough to have watched one end. A star's mass sets almost the entire course of its lifespan. More mass means more gravity, which drives faster, hotter fusion at the core. Faster fusion means the fuel runs out sooner, no matter how much of it a star begins with. Less massive stars fuse far more gently, stretching a smaller store of hydrogen across an immense span of time. It is one of the simplest rules in astrophysics, and one of the most consequential. The heaviest stars burn out in a cosmic blink, some lasting only a few million years before ending in dramatic collapse. Smaller stars, by contrast, can persist for trillions of years, quietly outlasting galaxies, outlasting almost everything else in the observable universe. This vast difference in lifespan means the sky we see tonight is a mixture of extremes, brilliant giants living briefly and faint dwarfs living almost forever. Between these two kinds of stars lies the entire story of stellar survival. Nearly every genuinely ancient star astronomers observe today shares the same modest appearance. They are small, dim, and cool, nothing like the brilliant giants that populate so much of popular imagination. Their light is often reddish or orange, the color of a fire burning low and slow. This humbleness is not a limitation of our instruments, it is simply what survival looks like. The stars that lived long enough to become ancient did so by staying small and unremarkable. Our own sun, for all its warmth and familiarity, has a comparatively short life ahead of it. Its total lifespan is expected to reach only about 10 billion years before it swells into a red giant and fades. Many of the ancient stars described here have already existed longer than that, and will continue long after the sun is gone. It is a strange comfort to realize how young our nearest star still is. In cosmic terms, the sun is barely past its middle years. Scattered around the outer reaches of our galaxy are dense, spherical swarms of stars called globular clusters. Each one can hold hundreds of thousands, sometimes millions of stars, all bound tightly together by gravity. Within these crowded spheres, some of the oldest stars in the Milky Way sit closely packed, like ancient seeds gathered in one place. Their density gives them a soft, glowing hue when viewed through even modest telescopes. These clusters have become natural laboratories for studying the deep age of stars. Globular clusters drift in slow orbits through the halo of the Milky Way, tracing wide paths high above and below the galaxy's crowded disk. This halo is a sparse, spherical region surrounding the spiral arms, home to some of the galaxy's oldest structures. Each cluster follows its own elliptical route, some dipping close to the core, others wandering into the emptiness beyond. Unlike the disk's orderly rotation, halo orbits can tilt in almost any direction. It marks an older, more solitary neighborhood within the galaxy's architecture. The Milky Way is known to hold roughly 150 of these clusters, each one a separate reservoir of ancient starlight. Astronomers have cataloged them one by one, mapping their positions like scattered lanterns around the galaxy's edge. A few sit hidden behind clouds of dust near the galactic center, making them hard to count precisely. Others hang far out in the halo, easily visible even in modest telescopes. Together, they form a faint, ancient scaffolding around our galaxy's brighter, younger disk. There is nothing to hold on to right now, only the warmth spreading through your limbs as they settle deeper into the bed. Let your shoulders sink into that warmth, let your jaw loosen, let the small tensions of the day melt away like light fading from an evening sky. Each breath arrives a little slower now, a little warmer, carrying you further from wakefulness. You do not need to follow any thought to its end. Just rest inside this warmth and let the mind grow still. Globular cluster stars formed during one of the earliest bursts of star formation, the young universe ever produced, not long after the first heavy elements began to spread through space. Whole clouds of gas collapsed together within a short span, giving birth to hundreds of thousands of stars almost simultaneously. This shared origin is why cluster stars often share strikingly similar ages and chemistries. It is as though an entire family was born within the same brief season. That season, though brief, happened more than 12 billion years ago. Astronomers can plot every star in a cluster on a chart of brightness against color, producing what is called a color magnitude diagram. Along this diagram, stars trace a curving path called the main sequence, where most stars steadily burn hydrogen through most of their lives. At a certain point, the brightest remaining stars begin to peel away from that path, a location known as the turn-off point. The exact position of this turn off depends only on how long the cluster stars have been burning fuel. By measuring where that bend occurs, astronomers can read a cluster's age directly from its light. To turn that diagram into a precise number, astronomers use a method called isochrone fitting. Theoretical curves called isochrones represent how stars of a single, shared age would appear across every mass and color. These model curves are laid over the cluster's real, measured stars, adjusted gradually until the fit becomes close. Where model and observation align most tightly, the corresponding age is taken as the cluster's own. It is a patient overlay of physics onto starlight, decades in the refining. Messier 4 counts among the closest globular clusters to Earth, resting in the constellation Scorpius at a distance of roughly 7,200 light-years. Its relative closeness makes it a favorite target for both amateur observers and professional researchers. Through a small telescope, it appears as a pale, granular haze, resolving into individual points of light under higher magnification. Because it lies nearby, its stars can be studied in unusually fine detail. That closeness has made Messier 4 something of a benchmark cluster in stellar age research. Within Messier 4, Astronomers have identified an unusually faint population of white dwarfs, the cooling embers left behind by stars that have already lived out their lives. Because white dwarfs fade at predictable, well-understood rates, the faintest ones among them mark the longest cooling times. Deep imaging, including observations from the Hubble Space Telescope, has traced this population down to its dimmest members. Their estimated cooling ages point to a cluster roughly 12 to 13 billion years old. These faint embers offer an independent check on ages measured through other methods. The cluster known as INGSI 6397 has undergone what astronomers call a core collapse, a slow crowding of stars into an extraordinarily dense center. Over billions of years, gravitational encounters pulled its heavier stars inward, tightening that region step by step. The result is a heart so packed that stars there sit far closer together than anywhere else in the cluster. This makes INGSI 63971 one of the most tightly bound stellar environments known nearby. It stands as a vivid example of how gravity slowly reshapes a cluster over cosmic time. Detailed studies of this collapsed cluster place the age of its stars at approximately 13.4 billion years, among the oldest ages estimated for any globular cluster. That figure emerges from careful turn-off measurements combined with isochrone fitting, cross-checked against its faint white dwarf population. Such an age places INGSI 6397's birth within the universe's own early childhood, not far removed from the very first galaxies. Standing at this age, its stars have witnessed nearly the entire history of cosmic time unfold around them. Few objects nearby carry such a direct link to that distant beginning. Omega Centauri stands as the most massive globular cluster known within the Milky Way, a glittering sphere containing nearly 10 million stars. Its sheer size sets it apart from every other cluster orbiting our galaxy, dwarfing typical clusters many times over. Visible to the unaided eye from dark southern skies, it appears as a faint, glowing smudge near the constellation Centaurus. Within its crowded heart, countless points of starlight blend into something resembling a pale golden mist. Few objects in the sky hold so many ancient suns within so small a space. This same glittering cluster may be the stripped remnant core of a dwarf galaxy once devoured by the Milky Way. Its stars show a range of ages and chemical compositions unlike any ordinary cluster, hinting at a more complicated past. Clusters usually form together in one burst, but this one appears layered, as though built from several generations. Its unusual rotation and elongated shape further support the idea of a separate earlier galaxy. If that is true, Omega Centauri would be a fossil heart, all that remains of a galaxy the Milky Way once absorbed. 47 Tucanae ranks among the brightest globular clusters visible from Earth, second only to Omega Centauri in apparent splendor. Located in the southern sky near the small Magellanic Cloud, it glows as a dense, radiant ball of ancient light. Its stars number in the hundreds of thousands, packed into a sphere just a little more than 100 light-years across. Astronomers have used it extensively to study stellar evolution, given its brightness and relatively close distance. Through binoculars, it already reveals a hazy, luminous core. For a moment, let your attention drift toward the hush around you, the faint hum of a room settling into night. Nothing needs holding on to, no thought that needs finishing. Let your shoulders sink further into whatever holds you. Each breath can grow a little longer than the last, unhurried, without effort. The night does not ask anything of you. It simply continues, wide and unbroken, while you rest inside it. A star, officially designated HD 140283, carries a fitting nickname, the Methuselah star, after the biblical figure said to have lived longer than any other. Astronomers chose the name because its estimated age once seemed almost impossibly great. It belongs to a rare class of extremely metal-poor stars, born from gas barely touched by earlier generations. Though faint and unremarkable to look at, it has become one of the most studied stars in the galaxy. A humble point of light, it carries billions of years within it, almost unnoticed. The Methuselah star lies just under 190 light-years from Earth, making it remarkably close for something so ancient. That proximity places it well within our own galactic neighborhood, closer than many stars far younger than itself. Its relative nearness has allowed astronomers to measure its distance, brightness, and composition with unusual precision. Because it sits so near, its light reaches us having traveled for less than 2 centuries. In cosmic terms, that is barely any time at all, a brief hop compared to the star's own vast age. For a time, calculations suggested the Methuselah star was older than the universe itself, an age that made little sense within known cosmology. Early estimates placed it at around 16 billion years, well beyond the universe's own age of roughly 13.8 billion years. This apparent contradiction puzzled astronomers throughout the early 2000s, since nothing can be older than the cosmos that contains it. The mismatch pointed not to a flaw in the universe, but to uncertainties in how the star's distance and brightness had been measured. It became a puzzle, waiting for better tools to resolve it. Improved distance measurements, drawn from more precise satellite observations, eventually resolved the puzzle surrounding the Methuselah star's age. Once its true distance was recalculated with greater accuracy, its brightness and temperature could be reinterpreted correctly. That refinement brought its estimated age down into a range fully consistent with the universe's own history. The correction illustrated how sensitive stellar age estimates are to something as fundamental as distance. What once looked like a cosmic contradiction turned out to be a measurement waiting for refinement. Today, the Methuselah star's age is estimated at about 14.5 billion years, though a considerable margin of uncertainty remains attached to that number. Depending on the model used, its true age could plausibly range a billion years in either direction. Even with that uncertainty, it remains among the oldest individual stars ever measured with reasonable confidence. Its light began its long journey to Earth not long after the very first stars formed. Looking at it is, in a very real sense, looking near the beginning of everything. A star known as HE 1523-090, one offers a different way of reading stellar age, through the slow radioactive decay of thorium and uranium locked within it. These heavy elements break down at fixed, well-known rates, functioning much like a buried clock ticking since the star's birth. By measuring how much of each element remains, astronomers can calculate how long that clock has been running. It is a technique borrowed from the same principles used to date rocks here on Earth. Applied to starlight, it becomes a way of dating fire itself. This radioactive dating technique carries a long name: nucleocosmochronology. It simply means dating the cosmos through the decay of atomic nuclei. Thorium and uranium, forged in ancient stellar explosions, break down into other elements at rates fixed since the beginning of nuclear physics. By comparing what remains to what must have existed at formation, astronomers translate faint starlight into a number of years. The method turns a single spectrum into a timestamp reaching back toward the universe's earliest chapters. Using this method, the star known as HE 1523-0901 was dated at about 13.2 billion years old. Its thorium and uranium levels, measured with unusual precision, pointed nearly back to the universe's infancy. That places its formation only a few 100 million years after the very first stars are thought to have ignited. It remains one of the rare stars aged by radioactive decay rather than by brightness and color alone. Its glow carries a kind of memory, written in vanishing atoms. For a time, The star catalogued as H1327-2326 held the record as the most iron-poor star ever found. Discovered in the early 2000s, it startled astronomers with how little heavy material it contained. Its spectrum showed almost no trace of iron, the element usually used as a baseline for stellar chemistry. For several years, it stood as the clearest example of a star born when the galaxy had barely begun forging metals. Its faint light became a benchmark against which newer discoveries would later be measured. Its iron abundance turned out to be almost 1,000,000 times lower than the Sun's, a scarcity that pushed the limits of what instruments could even detect. Where the Sun holds roughly 1 iron atom for every few 100,000 hydrogen atoms, this star held far less than 1 in many millions. Such extreme scarcity suggested it formed from gas touched by only the faintest trace of earlier stellar explosions. Astronomers described its chemistry as almost pristine, a near-direct sample of the universe's rawest material. In its faint light lingered an echo of the very first supernovae. Let your shoulders loosen into whatever is holding you, and let the warmth of your blankets sink deeper into your skin. There is nothing to work out tonight, no thought that needs finishing. Let your breathing find its own unhurried rhythm, and let the weight of the day slide away like sand loosening its grip. The room grows warmer, dimmer, farther from any need for words. You can simply rest here, held by nothing more than returning stillness. A star known as SMSS03 13-6708 ranks among the most chemically primitive ever found. Discovered in a wide survey of the southern sky, its spectrum showed barely a whisper of heavy elements. Astronomers measuring its light found values so low that existing models struggled to explain them. It seems to preserve conditions from a time when the galaxy had scarcely begun forging anything heavier than helium. In many ways, it reads like a fossil imprint of the universe's earliest chemistry. Its iron content, when measured, appeared almost undetectable, hovering right at the edge of what instruments could sense. Where most stars carry a clear fingerprint of iron in their spectra, this one showed almost nothing where that fingerprint should be. The finding startled those who first reviewed it, since a near-total absence of iron challenges assumptions about how the earliest stars formed. The measurement did not mean no iron existed at all, only that its trace was smaller than anything seen before. It stood briefly as a boundary marker for how metal-poor a star could possibly be. This unusual chemical pattern suggests the star formed from gas touched by only a single early supernova, rather than by many generations of overlapping explosions. The ratios of certain elements matched theoretical models of one massive first-generation star collapsing and scattering its material outward. If the interpretation holds, this star offers something remarkably rare, a nearly direct sample of a single supernova's leftover ash. It is less a blended mixture, and more like a single brushstroke from the universe's earliest chemical painting. That simplicity is part of what makes it so valuable to study. Tafo's star, discovered in 2011, stands as another remarkably iron-poor object in this ongoing search. Named after the astronomer who led its identification, it was found through careful analysis of a faint point of light in a wide sky survey. Its measured iron abundance placed it among the most extreme examples known at the time. The discovery reinforced a growing pattern that the earliest generations of stars left behind chemical traces almost too faint to read. Each such find added another data point to a slowly emerging portrait of the young universe. That star may have formed from gas enriched by only one or two earlier generations, an almost minimal amount of chemical seasoning. Its abundances of carbon and other light elements hinted at a formation environment barely touched by nuclear fusion's slow accumulation. If true, It represents one of the simplest chemical recipes ever found in a surviving star. Such simplicity offers a rare window into conditions just after the universe's very first generation of stars had lived and died. It is a quiet leftover from a nearly unmarked page in cosmic history. Bright and relatively close by, HOD 122,563 is a metal-poor red giant that astronomers often use as a touchstone. Its light is easy to gather, its spectrum well-studied, its distance well-measured. Because it sits nearby and shines brightly enough for detailed study, researchers treat it as a calibration point, a known quantity against which fainter, more distant metal-poor stars can be compared. It serves as a steady anchor for much of the broader search for even older, dimmer relics. Cairl's star carries an unusual richness of rapid neutron capture elements, even though its iron content remains remarkably low. Elements like europium and gold appear in far greater proportion than iron, an imbalance rarely seen so clearly. The pattern puzzled astronomers when first measured, since iron and these heavier elements usually rise together. Instead, this star seems to preserve a moment when a violent, rare event scattered heavy elements before iron had fully accumulated. Rapid neutron capture elements form in the most violent corners of the cosmos, places where atomic nuclei absorb neutrons faster than they can decay. Neutron star mergers, two ultra-dense remnants spiraling together, can produce these elements in an instant. Certain rare, especially energetic supernovae may do the same. Either event floods surrounding space with freshly made gold, platinum, and other heavy elements, later gathered into the next generation of stars. This same pattern, found sprinkled through many old stars, traces some of the universe's earliest nucleosynthesis. Wherever it appears, it marks a moment when heavy elements formed in one sudden, decisive event, rather than accumulating slowly over generations. Comparing this pattern across many ancient stars lets astronomers piece together how often such events occurred in the universe's youth. It is a chemical echo, repeated star after star, older than the galaxy's spiral shape. Certain ancient stars display a curious mix of abundant carbon alongside very little iron, a combination astronomers describe simply as carbon-rich, metal-poor stars. Carbon lines appear unusually strong in their spectra, standing out clearly despite the star's overall metal poverty. This mixture shows up more often than expected among the earliest stars found so far. Its cause is still being pieced together, one spectrum at a time. For a while, let the sounds around you fade to almost nothing. Let your ears rest, as though listening to something very far away, something too distant to ever quite arrive. There is no need to catch it, no need to understand it. Just let the hush settle over the room, over your shoulders, over your closed eyes. Let it carry you further from thought, further from the day, into rest. Extra carbon in these carbon-rich, iron-poor stars may not have formed within the star itself. A nearby companion star, transferring material across space, could have donated it during a long-ago phase of mass exchange. Alternatively, an early supernova rich in carbon might have seeded the gas cloud the star was born from. Either path suggests these stars are shaped as much by their neighbors and birth environment as by their own nuclear furnaces. Another ancient halo star, catalogued as BD plus 17 degrees 3248, has drawn attention for its usefulness in radioactive dating. Like other thorium and uranium-bearing stars, its slowly decaying elements offer an independent clock, ticking since the moment of its formation. Researchers have used its abundances to check age estimates derived through other methods. Its readings broadly agree with ages found elsewhere, adding confidence to the wider timeline being assembled. Enhanced levels of elements like magnesium and calcium turn up in many of the oldest stars studied so far. These alpha elements, forged in the rapid, explosive deaths of massive early stars, appear in higher proportion than they do in younger, sun-like stars. Their abundance offers another clue about the kind of stellar deaths that enriched the early galaxy. A high ratio of these elements to iron often signals an old, rapidly formed star. A few primitive stars have turned up somewhere unexpected, the thin, orderly disk of the Milky Way, rather than its sprawling halo. Most ancient stars drift on scattered, tilted orbits far from the galaxy's flattened plane. Finding old, metal-poor stars moving smoothly within the disk itself raises open questions about how early the disk began forming. It suggests the galaxy's structure took shape earlier, and perhaps more gradually than once assumed. The halo of the Milky Way preserves debris of the galaxy's earliest formation, like sediment settling at the bottom of an ancient river. Long before spiral arms took shape, matter fell inward, merged, and scattered outward again. Some of it never gathered into the disk at all, remaining suspended in this sparse outer region. Stars born in that first chaos still drift there now, their light a record of a galaxy still finding its form. Gene. Dwarf galaxies orbiting the Milky Way also host extremely old, metal-poor stars, small satellite worlds circling their much larger neighbor. Each dwarf galaxy formed and enriched its own gas independently, following its own timeline. Because these tiny galaxies evolved at such an unhurried rate, their oldest stars can rival, or even exceed, the age of stars found within our own halo. They offer another vantage point on the universe's earliest chemistry. The Sculptor dwarf galaxy contains some of the most primitive stars found outside our own halo, drifting far beyond the Milky Way's outskirts. Its stars carry iron levels so low they rival the most ancient halo stars ever catalogued. Sculptor itself is small and faint, a modest galaxy easily overlooked against the southern sky. Yet within its stars lies chemistry reaching back toward the universe's very first generations of enrichment. Segway 1 is an ultra-faint dwarf galaxy whose stars show almost no chemical enrichment at all, as if time paused shortly after their birth. It ranks among the darkest, most diffuse galaxies ever confirmed, containing only a few hundred visible stars. Despite its faintness, its chemical simplicity makes it remarkable, a near-pristine sample of gas from the universe's youth. Few places offer such an unfiltered glimpse into conditions before heavy elements became common. Ultra-faint dwarf galaxies may be frozen relics of the universe's first galaxies, small pockets of star formation that began and then largely stopped. Their weak gravity could not hold on to gas for long, cutting off further star birth almost as soon as it started. What remains are stars formed in that brief window, chemically simple and essentially unchanged since. Studying them is like glimpsing a snapshot of galaxy formation still developing, never quite finished. Some ancient stars are hidden within the Milky Way's dusty, crowded bulge, tucked behind clouds of gas and starlight near the galactic center. Dust there absorbs and scatters visible light, making these old stars difficult to find and study. Infrared observations help astronomers see through that obscuring haze to the faint stars beyond. Even in the galaxy's busiest, most congested region, remnants of its earliest history apparently endure. For a moment, let your attention rest on sound rather than thought. Perhaps a clock ticks somewhere in the room, or wind moves faintly beyond the window. Let that distant sound be the only thing you follow, nothing else required of you. With each breath, the space between sounds grows wider, and your body sinks further into stillness, needing nothing more than to remain exactly where it is. Ancient stars near the galactic center hint that old stars persist even within the galaxy's crowded core, not only its sparse outer reaches. Surveys peering through gas and dust have identified metal-poor stars orbiting deep within that dense central bulge. Their presence suggests some of the universe's earliest stars settled inward long ago, joining a region shaped by billions of years of later activity. Even at the galaxy's busy heart, its oldest inhabitants remain. Old halo stars often follow highly elliptical or retrograde orbits, paths that loop far from the orderly rotation of the galaxy's disk. Some circle the Milky Way's center backward, against the direction most younger stars travel. These unusual trajectories likely trace back to the halo's turbulent origins, shaped by mergers and gravitational encounters long before the disk settled into its current form. Their orbits remain a kind of motion fossil, preserving that ancient disorder. Some old stars' orbits suggest they formed in smaller galaxies, later absorbed by the Milky Way, rather than being born within our galaxy at all. Their velocities and directions cluster together in patterns distinct from native halo stars, hinting at a shared, separate origin. Astronomers can sometimes trace these clusters back to specific ancient collisions. Each grouping tells of a smaller galaxy, long since dissolved, whose stars now belong entirely to our own. Nearly 10 billion years ago, a smaller galaxy called Gaia Enceladus drifted into the young Milky Way and merged with it completely. Its ancient stars poured into the growing halo, carrying a separate chemical history within them. This collision reshaped much of what we now call our galaxy's outer reaches. Many of the oldest stars circling above and below the disk were never born here at all. They arrived as travelers from a galaxy that no longer exists on its own. The Gaia spacecraft has mapped the positions, motions, and brightness of more than 1 billion stars across our galaxy. Launched to measure minute shifts in starlight with extraordinary precision, it has become an essential tool for dating the oldest stars we know. By tracking how a star moves and how far it truly lies from Earth, astronomers can calculate its age with far greater confidence than before. A single spacecraft, silently circling far from Earth, now anchors much of modern stellar archaeology. Stellar spectroscopy reads the fingerprints hidden within starlight, revealing exactly which elements a star contains. When light passes through a prism or diffraction grating, it separates into a rainbow marked with dark lines, each one a signature of a specific atom. By studying these lines, astronomers can tell whether a star is rich in iron or almost entirely without it. This simple trick of light lets us read a star's composition from thousands of light years away. Reading a star's light this finely can reveal elements present at only a few parts per billion, an almost unimaginable faintness of signal. High-resolution spectrographs spread starlight across enormous detail, separating wavelengths so precisely that even trace amounts of rare elements leave a visible mark. For the oldest, most metal-poor stars, this sensitivity matters enormously. It lets astronomers detect faint traces of elements that barely exist within them at all. Large telescopes, such as the Very Large Telescope in Chile and the Keck Observatory in Hawaii, spend many nights hunting for faint, ancient stars. Their wide mirrors gather enough starlight to capture detailed spectra from stars far too dim for smaller instruments. Perched atop remote mountains, these observatories sit above much of the atmosphere's blur. Night after night, their instruments gather the faint light of stars that formed while the universe itself was still young. James Webb Space Telescope was built partly to search for indirect evidence of the earliest stellar populations, the ones no instrument has directly seen. Its infrared eyes can peer through cosmic dust and immense distance alike, reaching toward light from the universe's first several hundred million years. Rather than finding a single ancient star, it looks for entire galaxies glowing in patterns that hint at extremely primitive stars within them. It becomes a distant echo detector, tuned to the faintest whispers of cosmic dawn. Indirect evidence for the earliest stars sometimes comes from extraordinarily distant, gravitationally lensed galaxies. When a massive foreground cluster bends and magnifies light from something far beyond it, faint background galaxies become visible that would otherwise stay hidden. Within some of these magnified images, astronomers glimpse unusual patterns of light that may hint at extremely metal-poor stars burning within. It remains an open question whether any of these signatures truly trace population restars, but the search continues. Autry, let warmth settle over you now, spreading from your chest into your arms, down through your hands, into your legs, and finally into your feet. There is nothing to hold on to, nothing to solve, just the slow spread of warmth, like sunlight moving across a wall at midday, filling each part of you in turn. Let your breathing follow that warmth, unhurried, heavy, settled. You are allowed to rest exactly like this, for as long as you need. White dwarfs act as cosmic clocks because they cool at slow, predictable rates once nuclear fusion inside them stops. A white dwarf is the compact leftover core of a star like the Sun, radiating away stored heat with nothing left to burn, because physics predicts precisely how fast that heat escapes. Astronomers can measure a white dwarf's temperature and calculate how long it has been cooling. The dimmer and cooler it appears, the older it almost certainly is. Even the coolest, faintest white dwarfs found within globular clusters mark some of the oldest stellar remnants known to exist. Buried among thousands of brighter stars, these dim embers have been cooling for well over 10 billion years, slipping toward the very edge of detectability. Locating them requires extremely long telescope exposures and remarkably steady conditions. Once found, their temperatures translate almost directly into an age for the entire cluster surrounding them, confirming what other methods suggest. White dwarf cooling curves offer an independent estimate of age, separate from the methods astronomers use elsewhere. Because cooling rates are governed by well-understood physics, a star's remaining heat translates almost mathematically into elapsed time. When this cooling age lines up with ages drawn from cluster turn, off points, or isochrone fitting, confidence grows that the underlying figure is real. Agreement across such different techniques is one of astronomy's most understated satisfactions. Asteroseismology studies the tiny pulsations rippling across a star's surface to reveal what lies hidden within. As gas inside a star churns and settles, sound waves travel through its layers, causing the whole star to swell and shrink by minuscule amounts. By measuring these faint oscillations in brightness, astronomers can infer a star's internal structure, density, and composition. From that hidden architecture, remarkably precise estimates of stellar age can emerge. Starquakes rippling through red giant stars let astronomers listen to what stirs inside them. As a red giant swells outward, its interior resonates with sound waves bouncing between its core and surface, encoded in tiny flickers of brightness. Analyzing these flickers reveals whether the star is burning hydrogen in a shell or helium in its core, narrowing its age considerably. In this way, distant starlight becomes a kind of trembling signal from far within. Kepler and TESS, two space telescopes built to hunt for distant planets, gathered years of brightness data that proved equally valuable for astroseismology. Both watched countless stars continuously, recording the subtle flickers caused by internal pulsations across long, uninterrupted stretches of time. That monitoring, originally aimed at finding planetary transits, turned into an unexpected treasury of stellar ages. Old red giants throughout the galaxy have had their interior clocks read this way. A number of the universe's most ancient stars show puzzlingly low amounts of lithium in their outer layers. Lithium is a fragile element, easily destroyed by heat once dragged deep into a star's interior. Its scarcity, or abundance, offers another subtle clue toward a star's age and history. Certain old stars hold on to more lithium than expected, while others hold almost none at all. Astronomers call this mismatch the lithium problem, a gap between predicted and observed abundances in the oldest stars. Theoretical models of the early universe predict a certain amount of primordial lithium should remain locked within ancient stellar atmospheres. Yet, actual measurements consistently show less lithium than those models expect. The discrepancy remains unresolved, a small persistent puzzle at the edge of Big Bang cosmology. Big Bang nucleosynthesis describes how, within the universe's first few minutes, protons and neutrons fused into the earliest atomic nuclei. This process forged hydrogen, helium, and a trace amount of lithium, setting the primordial recipe for everything that followed. Physicists can calculate precisely how much lithium this process should have created relative to hydrogen and helium. That predicted number becomes a benchmark against which real ancient starlight can be measured. Measuring primordial lithium within the oldest stars becomes a way of testing the universe's earliest chemistry against direct observation. If ancient starlight consistently shows less lithium than the models predict, something in our understanding of those first minutes may need revising. Perhaps stellar interiors destroy more lithium than expected, or perhaps the nucleosynthesis models themselves need refinement. Either way, each ancient star observed adds another data point to this ongoing conversation between theory and starlight. Let a distant sound carry you now, not a sound you can name, just a low hum somewhere beyond the room, steady and unbothered by time. Let your shoulders release into whatever is holding them, and let your jaw loosen, your eyelids grow heavy without effort. Nothing here requires your attention. The hum continues, faint and constant, asking nothing of you but to keep resting, exactly as you are. A number of the universe's oldest stars are subgiants, caught mid-transition as they leave the stability of their long hydrogen-burning years. Having exhausted the hydrogen fuel at their core, they swell gradually, while a thin shell around that core continues burning. This brief evolutionary stage offers astronomers a particularly sensitive marker of age, since a subgiant's temperature and brightness shift quickly compared to its earlier life. The Methuselah star itself belongs to this fleeting, informative class. A star's position on the Hertzsprung-Russell diagram reveals its evolutionary age. This diagram plots a star's brightness against its temperature, and where a star falls within that plot tells astronomers what stage of life it has reached. Young stars cluster along a steady, predictable path called the main sequence. Older stars drift away from that path as their cores change, tracing a story written in light and heat, one that patient study can read like a timeline. The oldest stars are almost always poor in metals, yet not every metal. Poor star shares the same age. Low metal content usually points toward an early birth, since the universe had not yet built up heavier elements. But a star's chemistry depends on its birthplace as much as its birth time. Two stars with nearly identical faint traces of iron might still differ in age by hundreds of millions of years. Age and metallicity move together, but never in perfect step. Early enrichment across the young galaxy happened unevenly, in scattered pockets rather than one smooth wave. A star born in a pocket touched early by supernova debris might carry more metals than one born just as ancient, but in a quieter, untouched region. The correlation holds roughly, yet history left room for exceptions. Across the newborn galaxy, different regions filled with heavy elements at different speeds. Some clouds sat near clusters of massive, fast-dying stars and absorbed their scattered elements quickly. Others drifted farther from that activity, remaining nearly pristine for much longer stretches of time. This patchwork of enrichment means metallicity alone cannot always separate one ancient star's true age from another's. The most primitive stars earn a fitting nickname among those who study them: stellar fossils. Like fossils pressed into ancient stone, these stars preserve a record of conditions from the universe's youngest days. Their surfaces still carry the faint chemical signature of the gas clouds that first gave them form. Little has changed within them since, leaving that early imprint remarkably intact. Reading the chemistry locked inside these fossils resembles a kind of archaeology, only the artifacts are stars instead of shards of pottery. Each element detected in ancient starlight becomes a clue about the conditions long before that star was born. Layer by layer, astronomers reconstruct which supernovae came first, which elements formed when, and how the galaxy slowly built its chemical inheritance. This entire field of study carries its own fitting name, stellar archaeology. Researchers within it treat starlight the way archaeologists treat buried layers of Earth, each spectral line a marker of some distant, formative event. The comparison is not just poetic. The methods, patience, and careful cross-referencing required mirror those of any excavation, only conducted across light years instead of meters of soil. No confirmed population 3-star has ever been found, despite decades of dedicated searching. Astronomers have scanned deep skies with powerful instruments, hoping to catch even one surviving example of that first massive generation. Every candidate examined so far has shown at least trace metals, meaning it belongs to a later, enriched generation instead. The universe's very first stars remain, for now, a chapter known only through theory. Some theorize that a few population 3-stars might still exist, undiscovered, drifting somewhere at the universe's furthest fringes. Extremely low-mass versions of these ancient giants could, in principle, still be burning today, virtually unchanged since their birth. Finding even one would mean encountering starlight tied directly to the earliest moments of cosmic history. For now, this remains an open possibility rather than a confirmed discovery. There is nothing left to learn tonight, only warmth to settle into. Feel the weight of a blanket, real or imagined, resting over you like the hush of deep space itself. Let warmth spread through your chest, down through your arms, into your fingertips, and further still. Your thoughts can loosen now, drifting the way starlight travels across unimaginable distance, arriving without effort, asking nothing of you but rest. Computer simulations suggest a few population 3-stars, if they formed with unusually low mass, could theoretically still be shining somewhere in the universe today. Most of that first generation burned brilliantly and briefly, gone within a few million years. But a rare handful, born small and slow, might have avoided that swift ending. Such stars would carry no measurable metals at all, a direct echo of the universe's very first light. Such surviving population 3-stars would be exceedingly faint, dimmer than nearly every star catalogued so far. Their low mass keeps them burning steadily, but that same slowness keeps them nearly invisible across cosmic distances. They would resemble countless other small, cool stars, hiding among them without any obvious sign of their true ancient nature. Only their chemistry, utterly free of metals, would ever give them away. Finding even one true population, 3-star, would revolutionize our understanding of cosmic dawn. It would move that early era from careful theory into direct, measurable observation. Every assumption about the first supernovae, the first heavy elements, and the first pathways toward later stars would gain a firm anchor. For now, that discovery remains a hoped-for milestone, still waiting somewhere in the depths of the sky. The oldest confirmed stars all belong to population 2, born after the universe received its first faint traces of heavier elements. Unlike the purely theoretical first generation, these stars carry just enough enrichment to leave a readable chemical signature. They formed within the first billion years, gathering into the ancient clusters and halo streams astronomers study today. Every confirmed ancient star, without exception, still traces back to this second generation. Inside a number of ancient globular clusters, distinct stellar generations sit side by side, sharing the same crowded sphere of space. Rather than a single burst of birth, these clusters reveal layered chemical differences among their stars. Some stars show heavier enrichment in elements like sodium or aluminum than their neighbors. This layering hints that star formation inside a cluster was not always a single, tidy event. Multiple populations within a single cluster suggest repeated bursts of star formation, stretched across long stretches of time. An early generation likely enriched the surrounding gas, which then collapsed again to form a second wave of stars. This cycle could have repeated more than once within the same gravitational well. Each burst left its own subtle chemical fingerprint, still readable today in the light of individual stars. The cluster known as NGC 2808 shows at least 3 distinct stellar populations, each with its own chemical identity. Detailed studies of its stars reveal variations in helium and other light elements far beyond what a single uniform birth could explain. Astronomers see it as a vivid example of how complex the early lives of these ancient clusters could be. Its stars, though similar in age, are far from chemically identical twins. Some old cluster stars carry chemistry altered by material already processed inside earlier generations of their own cluster. Elements like helium and nitrogen appear enriched beyond what the original birth cloud alone could explain. This suggests some of that material came from stellar winds or ejected gas recycled within the cluster itself. In a sense, these ancient stars were partly built from the outer layers of stars that came just before them. Blue stragglers are old stars that appear deceptively young, sitting far bluer and hotter than their true age would suggest. Inside dense clusters, one aging star can pull matter from a nearby companion, gaining fresh fuel it should never have received. That stolen material reignites fusion processes that had already begun slowing down. The star effectively borrows time, appearing youthful while its true history remains ancient underneath. 2 aging stars can also merge together, forming a blue straggler and effectively resetting the clock on its appearance. The combined mass reignites core fusion at a faster, hotter rate than either star managed alone. From a distance, this merged star looks freshly born, glowing with youthful blue light. Yet its material predates nearly everything else surrounding it in the same ancient cluster. Let the warmth already inside your body remind you there is nowhere else to be. Feel it pooled in your hands, your feet, the low curve of your spine. There is no clock counting down, no thought that requires an answer tonight. Let each breath grow a little longer than the one before it, as if the night itself were exhaling with you. Nothing here needs solving, only resting, held in that same warmth, drifting further from waking. Determining a true age for blue stragglers is notoriously difficult, even for careful astronomers who study them closely. Their reset clocks make ordinary aging methods unreliable, since their outer layers no longer match their real history. A star born ancient can appear, on paper, startlingly young. Researchers must lean on subtler clues instead, the pulsations of nearby companions or finer chemical traces hidden deep within their light. Horizontal branch stars represent a late evolutionary stage, common among old, metal-poor clusters scattered through the galaxy's halo. Having already burned through their hydrogen, these stars now fuse helium in stable, steady cores. They form a distinct band across a cluster's diagram, glowing with a golden, even light. Their presence alone helps mark a cluster as ancient, since only enough time can produce so many stars reaching this same late stage together. RRAL, variable stars, appear often within globular clusters, brightening and dimming in a steady, repeating rhythm. Their light rises and falls across hours or days, tracing a pattern astronomers can read from enormous distances. Because their behavior stays so consistent, they help calibrate distances across the cosmos, becoming faint markers scattered through the halo. Wherever ancient clusters gather, these pulsing stars tend to appear among them. Our Lyrae pulsation periods link tightly to a star's true luminosity, a relationship noticed generations ago. The longer the pulse, the brighter the star actually shines, regardless of how dim it looks from Earth. This tight relationship lets astronomers calculate distance simply by timing a star's rhythm. It turns each pulsing star into its own small, dependable ruler, reaching across unimaginable stretches of space. Most of the oldest known stars drift within the outer halo of our galaxy, far beyond the crowded disk where the Sun resides. Out there, stars are sparse, orbits are wide, and each ancient sun moves largely alone. This sparse region preserved them, undisturbed by the crowding and collisions common nearer the galactic center. In the halo, time seems to move differently, thinner, stiller, closer to the universe's own beginning. A handful of old halo stars have been flung into intergalactic space entirely, cast outward by close gravitational encounters long ago. A near pass beside a massive companion or an ancient collision between smaller galaxies can send a star free of its birthplace. These wandering ancients now drift through the emptiness between galaxies, carrying their old chemistry into the dark. They belong to no galaxy now, only to the space between them. Some hypervelocity ancient stars move fast enough that they may someday escape the Milky Way's gravity entirely. Given enough time, their outward paths could carry them beyond the galaxy's edge, never to return. They would continue outward for eons, carrying billions of years of history into an ever emptier sky. It is an unhurried journey, one outlasting most other stars, most galaxies' current shapes, and perhaps much of the visible universe as it appears tonight. The Methuselah star, along with others like it, turns out to be a humble subgiant, rather than some blazing giant. It shines modestly, its light neither dazzling nor dramatic, easy to overlook among brighter neighbors. Despite carrying some of the oldest chemistry known, it offers no grand visual spectacle, only a small, steady point of light. Its significance lies entirely in its history, not its appearance. Many of the oldest known stars are, in fact, surprisingly unremarkable to look at, small and faint against far younger, brighter neighbors. There is no special glow marking their extraordinary age, no visible sign of the billions of years folded into them. They look like an ordinary point of light in a dark sky. Their age lies instead in their chemistry, waiting for careful instruments capable of reading it. Ancient low-mass stars shine with a dim, steady glow that has barely changed in billions of years. Their light output drifts only slightly, a whisper of variation across ages longer than the Milky Way's spiral arms have existed. No flares, no violent swings, just a patient, even burn. A telescope pointed at one tonight would see almost the same light that left its surface when Earth itself was still forming its first oceans. Let your shoulders sink now, heavier than a moment ago. Feel the mattress rise to meet the shape of you, taking each part of your weight in turn, heels, calves, the small of your back, the base of your skull. There is nowhere else to be held. Let that steady gravity do the work, and let your thoughts loosen their grip, drifting downward like the rest of you, unhurried, sinking. Despite their age, many of these ancient stars still fuse hydrogen in their cores today. Deep inside, protons still collide and merge exactly as they did when the star first ignited. The fire never paused, never flickered out. It simply burns at a pace so slow that entire cosmic ages pass unnoticed within it. In distant places at the galaxy's edge, some cores are still doing the same steady work they began before the Earth existed. Some ancient stars have already exhausted their core hydrogen and moved on to the red giant branch. Their outer layers swell outward, cooling to a deep orange as the core contracts and heats beneath them. This is a natural next chapter, not an ending, one that unfolds over hundreds of millions of years. Seen from afar, such a star glows larger and redder than it ever did in its long youth. A few of the oldest stars now fuse helium at their cores, resting on what astronomers call the horizontal branch. Having survived their red giant swelling, they settle into a smaller, steadier phase, burning helium into carbon and oxygen. This stage offers a rare, stable pause in a star's long transformation. It is here, on this branch, that some of the most ancient stars in the galaxy sit, caught between one identity and the next, resting in an unassuming glow. Age estimates for the oldest single stars carry uncertainties of 1 billion years or more. A star said to be 13 billion years old might, in truth, be anywhere from 12 to 14. This is not a failure of the science, but an honest reflection of how difficult these measurements are. Even our best instruments are reading extremely faint light, stretched across distances that defy easy certainty. Distance errors, chemical models, and unproven physics assumptions all blur these ancient ages. Even a small error in how far away a star sits can shift its calculated age by a great deal. The chemical mixture presumed inside a star, and the way convection carries heat through its layers, add further layers of guesswork. Each assumption carries its own small shadow of doubt. Maya parallax measurements have sharply reduced age uncertainties for many of these ancient stars. By measuring the tiniest shifts in a star's position as Earth orbits the Sun, the spacecraft pins down distances with remarkable precision. That improved distance, in turn, tightens every age calculation built upon it. What was once an estimate spanning billions of years narrows, gradually, into something far more trustworthy. Before Gaia, distance errors alone could shift an estimated stellar age by billions of years. A star's true position, measured only roughly, left room for wildly different ages to seem equally plausible. Two astronomers studying the same star could reasonably disagree by an entire cosmic epoch. It was, in truth, an old and familiar limitation, one astronomy carried for generations before finally being eased. Improved opacity and convection models continue to refine stellar age estimates even now. Each generation of physics brings a slightly clearer picture of how light moves through a star's interior and how heat rises through its layers. These small refinements rarely make headlines, yet they steadily sharpen every age assigned to the oldest stars. The picture is never finished, only ever a little more precise than before. Every star's age, however ancient, runs up against one absolute boundary. No star, no matter how faint or how old its chemistry appears, can be older than the universe that made it. That upper limit sits near 13.8 billion years, the age of time itself as astronomers currently understand it. Any measured stellar age must fall beneath that ceiling, or something in the reckoning has gone astray. This boundary silently checks every age astronomers ever assign. A star discovered older than the universe would not simply be surprising. It would mean something fundamental has gone wrong in cosmology itself, a distance mismeasured, a stellar model flawed, or perhaps the universe's age itself in need of revision. Such a discovery would ripple outward, unsettling assumptions astronomers have relied on for decades. So far, no star has crossed that threshold and held there. Each near miss has instead revealed an error waiting to be corrected. For a while now, let the day's weight simply melt away. Feel warmth spreading through your shoulders, down your arms, into your fingertips, as if sunlight itself had settled into your skin. There is nothing left to solve tonight, nothing to hold on to. Let your breath grow long and unhurried, each exhale sinking you a little deeper into the mattress. Rest here, warm and unburdened, for as long as you need. Long before its true age was ever suspected, the Methuselah star sat catalogued among thousands of ordinary points of light. Astronomers first recorded it in the early 1900s, noting only its position and brightness. No one then imagined it carried some of the oldest surviving matter in the galaxy. Decades of spectroscopy and distance refinement were needed before its remarkable age came into focus. It waited, unnoticed, for the tools that could finally read its history. Independent checks using astroseismology have helped confirm the Methuselah star's revised age. By measuring tiny oscillations rippling through its outer layers, astronomers can infer its internal structure with striking precision. These star quakes act almost like a second, separate clock, unrelated to distance or brightness measurements. When the asteroseismic age matched the age drawn from Gaia's distance correction, confidence in the star's antiquity deepened. Two very different methods, arriving at the same ancient number. Hunting for the oldest stars does more than satisfy curiosity about the past. Each confirmed ancient age serves as a modest test of the standard cosmological model itself. If the oldest stars consistently fall within the universe's known age, the model holds firm. If they did not, cosmologists would need to rethink something basic about how the universe began and grew. So far, star after star has passed this test, reinforcing rather than undermining the larger picture. Some of the faintest ancient stars can only be studied using the largest telescopes on Earth. Their light, dimmed further by billions of years and vast distance, arrives almost too faint to register. Instruments like the Very Large Telescope or Keck Observatory gather enough of that light to split it into a spectrum. Without such immense mirrors, the chemical fingerprints of these ancient stars would simply stay hidden. Their faintness is, in a way, part of their honesty about age. Tomorrow's giant telescopes hope to find stars even older and fainter than any known today. Instruments many times larger than current observatories are being designed specifically to catch the dimmest, most metal-poor light in the galaxy. Astronomers expect these tools to uncover relics from star-forming episodes closer still to the universe's beginning. Each new generation of telescope has pushed the record a little further back. The oldest known star today may not hold that title for long. Chile's Atacama Desert, one of the darkest and driest places on Earth, is now home to the construction of the extremely large telescope. Its primary mirror, built from many hexagonal segments, will span nearly 40 meters across once complete. High, dry air and pitch. Black skies make this stretch of desert ideal for gathering the faintest starlight. When finished, it will be the largest optical telescope ever built, aimed in part at stars from the universe's earliest chapters. Above Earth's atmosphere, spectroscopy avoids the shimmer and haze that blur faint starlight from below. Air itself, endlessly shifting and refracting, distorts and dims the light of the most ancient faraway stars. Telescopes placed in space sidestep the turbulence entirely, capturing steadier, cleaner spectra. This clarity matters most for the faintest relic stars, whose chemical signatures are already close to the limit of detection. Every atom of hydrogen between here and a distant star adds its own small blur. Only about one star in every 100,000 halo stars is thought to carry the extreme chemical poverty astronomers look for. Most halo stars, though old, still carry measurable traces of later generations of chemistry. The truly ancient ones, poor in iron beyond a 10,000th of the Sun's share, are rare specks within an already rare population. Finding them means searching through a crowd where nearly everyone looks almost the same. Only the faintest chemical whisper sets the rarest ones apart. Locating new ancient stars means scanning millions of points of light across enormous stretches of sky. Wide-field surveys photograph broad regions of the galaxy over and over, cataloging faint colors and brightness for every star they capture. Among those millions, only a rare handful will show the pale chemical signature of true antiquity. Astronomers sift through the vast majority to isolate a precious few. It is careful work, measured in years rather than nights. Machine learning algorithms now assist in sifting through enormous stellar catalogs, searching for the subtle color signatures of metal-poor candidates. Trained on already confirmed ancient stars, these programs learn to recognize faint patterns of light that once took specialists years to notice by eye. They scan millions of entries in moments, flagging the most promising handful for closer study. Human astronomers then take over, confirming or setting aside each candidate. The old task of stargazing has gained a tireless digital companion. For a while, let sound be the thing that carries you. Somewhere beyond this room, a clock ticks, or wind moves through unseen leaves, or nothing at all disturbs the hush of night. Let that faint hum settle into the background, steady and unbothered by anything you carry. Your thoughts can rest now, loose and unfollowed, drifting like far-off radio static fading into a single low tone. There is nowhere else to be, nothing else to hold. Let the sound outside become the sound of rest. The pristine survey searches specifically for the rarest, most iron-poor stars using a narrow band of finely tuned filters. Instead of scanning ordinary starlight, it isolates a thin sliver of the spectrum where certain elements leave their mark. This narrow focus lets astronomers separate promising candidates from the overwhelming background of ordinary stars. Named for the near-unspoiled chemistry it hunts, the survey has already turned up several of the most primitive stars known. Its filters see something the human eye alone never could. Follow-up observations, using high-resolution spectroscopy, confirm the candidates first flagged by broader photometric surveys. A wide survey can only guess at a star's chemistry from its colors alone. Detailed spectra split that starlight into thousands of finely measured wavelengths, revealing the true abundance of iron and other elements. Many early candidates, promising at first glance, turn out to be ordinary stars once examined this closely. Only the rare few that pass this second test earn a place among the truly ancient. Each newly confirmed ancient star becomes one more data point on the long timeline of cosmic chemical evolution. Its measured abundances slot into a growing chart tracing how iron, carbon, and other elements accumulated across billions of years. A single star cannot tell the whole story, but 1,000 such stars, gathered over decades of careful searching, begin to sketch the shape of the early galaxy's chemical history. Every confirmed star sharpens that picture just a little. The chart grows more detailed with every careful discovery. Some ancient halo stars swing so far above the galaxy's flat disk that a single orbit takes hundreds of millions of years to complete. Their paths carry them high over the crowded plain where most stars remain, out into sparser, emptier space. From such distances, the Milky Way spiral would appear as a faint, glowing disk far below. These stars complete only a handful of orbits in the entire history of the universe. Time, for them, is measured in laps, so long they barely seem to move at all. A few of the oldest known stars carry a chemistry that suggests they were never born within the Milky Way at all. Their particular mix of elements does not quite match the pattern typical of stars formed in our galaxy's earliest disk or halo. Instead, it echoes the slower, different chemical evolution once found in smaller neighboring galaxies. These subtle mismatches act like an accent, a trace of somewhere else. It remains an open question exactly which vanished galaxy first gave them light. These so-called accreted stars were captured long ago from smaller galaxies that the Milky Way absorbed over billions of years. Each merger folded a foreign population of ancient stars into our own halo, blending distant histories into one shared structure. Some still drift on orbits that echo their original, now vanished home galaxy. Others have mixed so thoroughly that only their chemistry gives away their foreign origin. In this way, the Milky Way's halo is partly made of borrowed starlight. Chemical tagging can distinguish native Milky Way stars from ancient accreted ones. Astronomers compared dozens of elemental ratios at once, building a chemical fingerprint unique to each star's birthplace. Stars, born within the Milky Way's own early disk, share one subtle pattern. Stars captured from smaller, absorbed galaxies carry another, shaped by a slower, different enrichment history. Layer by layer, this fingerprinting sorts a shared population of ancient stars into separate ancestral threads. None of the oldest low-mass stars observed today are anywhere near dying. Despite ages stretching past 13 billion years, these stars burn hydrogen at a pace so measured that their cores remain far from exhaustion. Their nuclear furnaces sip fuel at a rate almost impossible to picture. A human lifetime witnesses less change in such a star than a single heartbeat changes an ocean. Whatever fate eventually finds them lies unimaginably far in the future, beyond anything astronomers can currently observe. Convective mixing in red dwarfs allows them to use nearly all their hydrogen fuel, not just the fuel held in their core. Inside these small stars, boiling currents of plasma constantly stir the interior, carrying fresh hydrogen down toward the fusion zone. Larger stars like the Sun cannot do this efficiently, so most of their hydrogen sits unused, stranded in outer layers. A red dwarf, by contrast, eventually taps almost its entire mass as fuel. This single mechanism is a major reason such stars can burn for such an immense stretch of time. The lowest mass red dwarfs alive today will outlive the Sun by enormous margins. Our Sun, a middling yellow star, will exhaust its core hydrogen in about 10 billion years and swell into a red giant. The smallest red dwarfs, by contrast, burn their fuel so efficiently and so faintly that 10 billion years amounts to only a brief opening chapter. Some will still be fusing hydrogen when the Sun has long since faded into a cooling white dwarf. Mass, more than anything else, decides how long a star's story runs. Let your shoulders settle into whatever is holding you right now. The mattress, a chair, the curve of a pillow. Feel a small warmth spreading from your chest outward, down through your arms, into your fingertips. There is nowhere else to be, and nothing left to solve tonight. Each breath draws that warmth a little deeper into your body, settling into your hips, your knees, the soles of your feet. Let the weight of the day dissolve into that warmth, and rest. Some models suggest the smallest red dwarfs could keep fusing hydrogen for 10 trillion years. That number is difficult to hold in the mind, since it dwarfs the current age of the universe many times over. If such a model proves accurate, these stars are, right now, only a tiny fraction of the way through their lives. 13.8 billion years, the entire history of everything we know, would be less than a single % of their total lifespan. Time, on this scale, stops behaving like anything familiar. Such stars would outlive every galaxy's current visible structure as we know it. Long before their fuel runs low, the graceful spiral arms of galaxies like our own will have merged, stretched, and rearranged themselves entirely. Galaxy clusters will drift apart as space itself continues to expand. The night sky, wherever it is still watched, will look nothing like it does tonight. And through all of that immense rearrangement, these small red stars may simply continue burning, undisturbed. When the last red dwarfs finally die, they will fade over unimaginable stretches of time into dim, inert black dwarfs. There will be no dramatic collapse, no explosion, only a gradual dimming as fusion finally ceases. A black dwarf holds no more nuclear fire, only leftover heat radiating away into the dark. Even that leftover warmth takes an extraordinary span to bleed away completely. What remains, in the end, is a cold, dark sphere drifting silently through whatever space still exists. No black dwarf has ever formed yet, since the universe is far younger than that process requires. The very fastest cooling white dwarfs still need far longer than the current age of the cosmos to darken completely. Every white dwarf now shining, no matter how faint, still radiates measurable heat and light. The black dwarf remains a purely theoretical endpoint, described in equations but never once observed. It is, in a strange sense, a future the universe has not yet had time to reach. The oldest living stars today are, in a sense, still just beginning their extraordinarily long lives. 13 billion years, though vast beyond ordinary comprehension, may be only a small opening movement in their story. Astronomers studying them are witnessing early childhood, not old age. If the smallest red dwarfs truly persist for trillions of years, then all the ancient stars found so far, however venerable they seem, remain remarkably young by their own standards. The universe's oldest light may, in truth, still be shining from stars that have barely begun. Studying these ancient stars lets us gaze almost directly at the chemical afterglow of the universe's first light. Their faint spectra still hold traces of that primordial glow, chemistry rewritten across billions of years, but never fully erased. In watching them, we are, in a real sense, witnessing the universe's earliest morning, still unfolding in starlight that only now reaches us. That old light has traveled farther than imagination reasonably allows, and tonight it settles somewhere near you, unhurried and unbroken. Rest now, beneath light older than memory itself. Good night.